electronics in new formats is what the world calls the growing industry of printed electronics. Lots of exciting demonstrations, developments, some hype and some reality, but the basic idea is let's develop new kinds of functional inks, such as those containing nanomaterials, quantum dots, other kinds of nanoparticles, and let's liaise them through existing printing technology, and let's create electronic functionality that can't be realized exclusively using rigid wafers, because you need things in new formats over larger areas, from new kinds of displays to new kinds of lighting and photovoltaics to perhaps the cheapest but most personal embodiment of electronics, having smart packaging. It can tell you when your food is spoiling, or perhaps optimize the supply chain and feed the world better. For all of the ingredients in these devices, it's important to make features that are finer and thinner. And to skip a few steps in terms of the perspective of industry, there's a need for high-speed, high-resolution printing technologies that can create, for example, micron-scale transistors. So it'd be really awesome if we could print lateral features on the dimensions of the wavelength of light and print photonic structures and so on and so forth. So this has inspired our work to look into the limitations of flexography, the limitations of this simple contact printing process for ink transfer. And ideally, if I took a rubber stamp, say it's just one feature on a flat stamp, I would want to put a thin layer of ink on the raised feature of my stamp, contact the stamp with the substrate, and split it apart so I leave this perfect thin layer of ink on the substrate entirely, or I could split it evenly and then refresh. But what happens in reality when you do flexography is you're limited to printing features of about a few tens of microns wide by fluid mechanics. And you can have two basic problems. One, you can have instability in the liquid film on the stamp. If you make your film too thin to make this thin printed layer, then the ink will de-wet the stamp surface and you have a broken feature. Or if you overload the stamp or apply too much pressure, you have issues due to liquid spreading beyond the stamp feature, as well as what's known as the coffee ring effect. The solids in your ink spread out on drying. And therefore, even though you can make very fine rubber stamps, you can't make micron scale features because you run into these limitations of ink transfer mechanics. So we were inspired by this problem and had the idea to develop a new stamp material for flexography. Using nanoporous stamps, and the simple idea is instead of holding the ink on the surface, you hold the ink within the volume of the microstructure, and therefore you might be able to print with greater fidelity. And that's what we've done in our lab, and the approach we've taken is to modify carbon nanotube-based microstructures to make these nanoporous stamps. So in a plate-to-plate fashion with just two facing substrates, the simple process is you produce nanoporous microstructures, as I'll show you. These are micro-scale building blocks containing a whole lot of carbon nanotubes that make them like little sponges. You fill the microstructures with ink by capillarity, you contact, and then you print. And locally, if I give you a schematic picture of the process, imagine that each microscale feature of the stamp like a whole bunch of little pen quills that are wetted with ink. And you can therefore make uniform mechanical contact between the stamp and your surface, and you can print a thin ink pattern, and then the solvent dries and your solid is left behind. And here's a very simple demonstration pattern, an array of square stamp microstructures and an array of printed ink patterns. And if you have one stamp microstructure, this is a little forest, as we call it, of carbon nanotubes, you can print a square ink pattern, in this case 20 by 20 microns on a side with relatively sharp corners. And if you're familiar with, say, the limitations of inkjet printing, where you print round droplets and they spread out and they recoil and they dry, you can't easily print square features resulted from liquid. And in this case, if you scan an AFM across the surface of this feature, after drying, in this case, the silver nanoparticles, you have fairly good uniformity. This one ends up at about 40 to 50 nanometers across its breadth. So we make these stamps from carbon nanotubes, and it's something we've worked on in my group since it started almost 10 years ago, and we've understood a good amount about how to make these vertically aligned nanotube forests, and this is just to give you the visual picture of the growth and environmental TEM video accelerated by 50x, where the nanotubes are growing toward us. So you put a thin film of metal on a silicon wafer, it breaks up into nanoparticles, and you introduce a hydrocarbon, and the nanotubes will start nucleating individually and then self-assemble into this vertical structure. This is a really fascinating example of competition between mechanics and chemistry, but in practice what this let us do is get better understanding of how to make these nanotube forests or microstructures in our lab and patterning catalysts by photolithography. They are microscale in height and foam-like, and if you control the gases in your furnace that you have in your lab rapidly and insert and remove the sample, you can grow structures to tens of microns height in a matter 1 or 2 minutes. So it makes the process fairly efficient, and if you want to grow them much taller, not for stamps but other applications, you can grow them up to a couple millimeters with limitations due to the catalytic lifetime. In order to make the nanotube forests useful as stamps, we need to do some engineering. So they don't work as we take them out of the oven, and we have to satisfy a few requirements. If you remember the schematic of the process in mechanical contact, we need good intimate nanoscale contact between the stamp and the substrate. So we need to make the stamp soft both on its surface and in the bulk. The other thing is we need to make the stamp wettable to the ink we choose, say a water-based colloidal ink, and we also need to make it, third, resilient to elastocapillarity. There's been a lot of studies of carbon nanotubes where beautifully you shrink up the nanotube forest using capillary forces that exist when a liquid meniscus recedes. So to achieve these functional stamps and achieve those 3 objectives, we plasma etch the nanotubes after we grow them. That makes the surface soft. And then we coat them with a conformal polymer by initiated chemical vapor deposition. Our collaborators do that for us. And we end up with these microstructured nanophore stamps that are soft and liquid stable. And the collection of data that's been evolving behind me shows the fact that after you evaporate liquid from the final stamp, the nanotubes don't shrink, whereas here the forest shrinks. And if you do mechanical testing comparing the surface and the bulk modulus, we're able to achieve a structure that's soft on the surface and soft in the bulk. So it's a good, appropriately squishy stamp to get this uniform nanomechanical contact. The simplest kind of feature structure you can print is metal lines. So if you want to make any kind of circuit or interconnect, imagine connecting to the touch pixels on your display, you would print lines, and this is just taking a stamp of carbon nanotube forest with linear features, and these are the ink, silver ink features that result in, and you let the ink be printed, you let it evaporate, and then you put the pattern in an oven because you have to anneal the nanoparticles into your final metal, and by optimizing the time and temperature, you can make conductive metal features that are, in this case, about 60% of the conductivity of bulk silver. So that's a basic test that this process works and produce high-quality conductive features. We're trying our best to study the real kind of process science behind this, and to first order, we can say that the top surface of the stamp is sort of this distribution of sharp tips, where each tip is 1 or more coated carbon nanotubes with an effective elastic modulus and therefore bending stiffness also based on its diameter. And what you want to do for good printing is you want to press the wet stamp into your opposing surface. So take this and flip it over and press hard enough such that all of the wet nanotubes are in contact. And then you have opportunity to print a uniform layer. And this is inspired by looking at the top surface of the stamp, and here are nanotubes, and here's nothing. You call this a honeycomb, and you can see groups of nanotubes together. So like all these wet tips need to be in contact. And this works pretty well to predict the fidelity of printing. This is a plot comparing experiments to this contact mechanic model where the vertical axis is the contact ratio and the horizontal axis is the contact pressure, and it basically says there's a range of about a tenfold range of pressure where we get good printing, where the printed feature matches the printed stamp. If pressure is too low, mechanical contact is incomplete, and rather than printing a solid square, you print this kind of random hollow pattern, and if pressure is too high, you overprint. So similar to what I said for rubber stamps, except now we're actually squeezing ink out of the microstructure, and this is where you want to print. And we're continuing to do experiments to really understand the dynamics of printing. I think it's an interesting coupled mechanical and fluids problem, and just to give you an example, we have a little microscope setup we built where we look through a lens upon which we're printing, and now I'm playing this high-speed video over and over, which is one individual square, and what we look for is we look for the precession of the wet interface as contact is made, and that is letting us understand the dynamics of printing and also the recession process once we remove the stamp, how much liquid is left there and how does it dry. And then we can do experiments like on this glass lens where the lens has a relatively large curvature relative to the array of pillars, and you can print this fingerprint, and with some imperfections we can relate the size and thickness of the printed ink layer to the local pressure based on contact pressure theory, and lets us study the effect of the local pressure on the thickness and fidelity of the printed layer in a larger area fashion. we're obviously interested in printing things other than simple silver inks. Like it would be really awesome to print functional materials, oxide semiconductors, and for example, we've shown simply using commercially available materials that you can print semiconducting quantum dots of different colors. These are core shell quantum dots. And then another thing you can do is print narrow and broad features at the same time. Those are just kinds of things you can't easily do in droplet-based printing processes because the layers are thicker that you print and the capillary forces dominate. And one interesting thing we found by comparing all these different materials is that the thickness of the layer that we print is pretty proportional to the concentration of particles we have in the ink. So by comparing all these different types of nanoparticles, and they're slightly different sizes and different material chemistries, we find that after the ink layer dries, when we use the same stamp pattern, same stamp preparation, we end up with a thickness of solid that is proportional to the starting particle concentration. And that's interesting to us in hinting that the mechanics of transfer are leaving sort of the same amount of ink, same volume of ink behind every time. And what we would like to do in our further work is not only understand what limits the resolution and the uniformity, but also how we can control the thickness. So can we get down, as here, to say printing essentially monolayers of nanoparticles, giving the opportunity to get individual colloidal layers, which might remain as is or might be zapped together by some energy source to make very thin semiconductors or metals. Or can we make thicker layers, because for a lot of things like RF devices, you actually want thicker layers. And these dimensions are very important to the functionality of of what's provided. The last thing I'll show you is a simple example of the possibility of scale up. So we wanted to start to study the mechanics of this as a continuous process. So we built a simple, what we call a plate to roll printing system, where here is the stamp, roughly 1 by 1 centimeter silicon wafer with a pattern CNTs on it. And this is a roller with a polymer film on the surface. And our little machine basically executes coordinated rotary linear motion. And this is a flexure, a simple compliant mechanism with a capacitance sensor underneath it, which lets us control and measure the printing force. And using this, we can do printing so far sort of up to the limit of the actuation system. And you'll just see it, the roller zap back and forth at real time. And this is about 0.2 of a meter per second. So the idea is that we could potentially use this as a stamp material in a flexographic printing system, and there's a lot of challenges in scaling up the process of growing CNTs and patterning the CNTs and robustness and so on of the ink loading, but it could be possible that this could be a continuous process that could print finer features. And what I've learned industry cares about is process metrics. Not only things like cost, but rate and resolution can be lateral and resolution can be thick. And so far our process compares in this following way. We found that using these nanoporous stamps, we can print features, and this is the best we've achieved, about an order of magnitude finer than existing flexographic technology using rubber stamps. This is, of course, not nearly as good as tip-wise methods, bit pen, polymer pen lithography, and other methods of micro-contact and nano transfer printing, but importantly, we've shown it's a fairly fast process. And this is lab scale, and a lot of this is industrial scale, but we feel that the intrinsic contact mechanics are advantageous here. And also in terms of printing thin layers, this is a metric we devised in terms of lateral feature size versus a normalized thickness, the transfer volume of ink per unit length, and we've exceeded existing advances in gravure printing and flexography, sort of lab scale stuff rather than industrial stuff, also by a reasonable margin. And I show this not to say it's better and we're proud of it, but because these simple fundamental insights, I think, can be very powerful in what it takes to scale something up and make a manufacturing process better. So I think time is running low, but I'll take maybe 5 more minutes to show you a few other things even more quickly that I thought could be related to the general discussion we're going to have later. And they all, except the last thing, still relate to the idea of using carbon nanotube-based surfaces, these soft interfaces at the micro scale. This is a video taken in an SEM, a micro compression test with a flat tip of a carbon nanotube micropillar about 20 microns wide, 20 microns high. And in this case, we've coated the nanotubes with a very thin layer of aluminum oxide. about 1 nanometer upon 10 nanometer diameter tubes in this microscale forest. And when we did this, we found that the nanotubes, as a collective, rebound from almost full compression, like 90% compressive strain, and they rebound fully. And this let us start thinking about pick-and-place technology. So this is a video of a machine, the kind of machine that's used to assemble pretty much every circuit board made. And when circuit boards are made, you take a whole bunch of rigid electronic components, some are simple passives and some are microprocessors, and you load them into these machines on tapes, and you have this high-speed robot that comes with mechanical hands and picks and places the PCB, all computer-driven. Another, to me, like really amazing manufacturing technology needed for scalability. And these machines can pick and place 21,000 components per hour, but there's a number here, minimum component size 400 microns by 200 microns. And I don't have an answer to this, but I've wondered lately, like, what limits that size? Why isn't it smaller? Why can't it be smaller? Because when Mark talks about origami machines or smaller RFID tags, or how much intelligence we can put into chips, if we could pick and place smaller things, we might be able to make amazing, really small devices, which could be cheaper or could be more functional at the micro scale as we're after. So how this all relates is just this slide, and the fact that we've started to study how to use these nanotube surfaces as what I'll call electroadhesives, which is a term that has been used to describe the use of electrostatics voltage to apply force to materials. And here's an experiment where we take an AFM tip with a conductive coating on it and apply a potential across a nanotube forest where the nanotubes are coated with a thin dielectric. And therefore, you get opposite charge between the coated nanotubes and the tip, and you do a mechanical test and compare a test without a voltage to a test with a voltage, and there's a significant pull-off force when the voltage is applied. Maybe obvious from a physical point of view. Basically, we're studying how to engineer these surfaces, their compliance and their roughness to enable a very high on-off adhesive ratio when we apply this voltage. The idea is that the alumina coating kind of blocks the intrinsic van der Waals adhesion between the surfaces, but if you apply voltage across it, you can get adhesion back. And we're interested in using these small nanotubes as stamps for placing very small devices. If I extrapolate to the macro scale, it's kind of like a gecko adhesive, but a gecko adhesive that's switchable. And so far we've been able to get roughly 10 newtons per square centimeter between 1 and 10, which is in the same realm of a gecko adhesive, but we haven't built a robot that can climb a wall. This is just the extrapolation for this adhesion. So this kind of surface engineering at fine scales is probably a pretty interesting for manufacturing as well. The last thing I'll show you is not nanotube related, but kind of printing related. I've gotten really excited about the possibilities for 3D printing in the past few years. I mean, it's likewise a bit of a buzzword, but if we can produce things on demand quickly in small quantities, I think will change how we think about our role in production and how much of something we need to make it viable. So one of my students has developed a really fast desktop 3D printer that can print little plastic objects in a matter of minutes rather than a matter of hours, and this is based on a little laser heated mechanism that we've been able to make very lightweight and attach to a gantry. Makes me think in that's the first microwave oven from 45 years ago when we could, cook something in 5 minutes in our kitchen. I think there's a profound difference if we can fabricate stuff fast. And maybe it's not at the macro scale, maybe it's at the nano scale. We've also started to think about how to kind of combine the principles of directed self-assembly or capillary directed assembly with the principle of 3D printing and extrusion. These are some recent experiments where we, with precision, we do something very simple, which is we take a colloidal solution of microbeads, of polymer beads, and we slowly extrude them out of a moving needle. So what you're seeing here is a fine glass capillary, and what you're seeing here is a solution of polymer polystyrene spheres being drawn down by evaporation-driven convection. As we move these apart, we can grow fairly tall colloidal crystals, polycrystalline colloidal structures up to a few millimeters or even a couple centimeters. And we've been trying to study some of the basic principles to grow these really, really tall self-assembled colloidal crystals. And I think there may be some interesting intersections here between macro scale, direct write fabrication and having microscale or nanoscale machines, or perhaps using some more exquisitely engineered colloidal materials in these techniques, whether we're thinking about here is just simple optical properties, structural color, from 190 nanometer particles to 280 nanometer particles, but perhaps there are some more sophisticated, interesting properties on the horizon. But combining the action of the machines to assemble themselves, as well as actions we can exert more readily using mechanical influence, might be something to look into in the future. And that's where I'll conclude. This is a picture of my group huddled around a really cool sculpture in the new math department wing at MIT. I've heard that they designed this expecting students to climb on it, and they determined via finite element analysis that it could hold 4 people. Yet they, of course, put out a sign that you should not climb it. Taking this picture involved getting a few of these people to stop shaking the sculpture. And in particular, I want to thank this guy, San-Ha Kim, who's been a postdoc with me since I came to MIT almost 4 years ago, and he's led a lot of this work and really been a cornerstone of our group. And thank you to all the others, our funding sources across our group, and thank you very much for your attention. Okay.
So we had a couple of people come up with some machines, and I've seen them when it's supposed to plot it on. It basically just sprays a sample onto a TDM grid, and the idea is to create really fine droplets, but you have to have a really nice dispersion, because otherwise you guys have too thick image or too thin. So what would be, I know that MIT had a couple of TDM groups that have something kind of
yeah. Haven't thought about it. Let's catch up later. Perhaps 2D patterning of liquids, or if there's something molecular in the liquid that would be interesting, might be an interesting application of what we do.
It is kind of, and there was an image that reminded me how a TM grid was when you freeze it. Yeah. So if you could control precisely what goes into each one of those squares, you can maximize your yield. You have something that's difficult to produce. At the same time, you have a chance to view it before you take it on this scope and see how it looks.
Cool. Yeah. Thanks. Let's talk later.
Do you have to optimize the version of the substrate for printing?
Yeah, so the wettability of the substrate is always important. You need the ink you're printing to be wettable to the substrate.
So the relative weighting between the carbon nanotube and the substrate that you have to optimize, right?
Yeah, so I can't say we've optimized that, but we've been able to devise conditions that are suitable for the inks we use so far.
Have you thought about using your understanding of nanotubes and printing technology to print components versus place them?
Can you explain what you mean by the difference between printing and
So
placing?
components are manufactured.
Yep.
But with your printing capability, using chemistry, is there any reason why you couldn't use that technology to print components on a circuit board rather than placing physical part components?
Sure. So that's a next. Yeah. I hear what you mean. So the next step in our flexographic printing is to print certain kinds of devices, right? Be able to print, kind of transistors, like requiring multi-layer printing, multiple inks, micron scale or thereabouts registry, compatibility between the layers, for sure.
It looked like from your plot that the smallest size you could do with the nanopores print heads was about 5 microns.
Yes.
What limits the small size? Why couldn't you make them smaller?
We're working on that. So far we've done 3 to 5 microns. So far it's been the lateral size of the stamp features we have created. You could argue, well, you could print something as small as an individual nanotube, because that would be the smallest little, pen point you could make. When we think about putting a bunch of things together here, how we grow the forest, how we coat them, what we know about their mechanics, I would say we could make something of a small few hundreds of nanometers where if I follow the same principle, you know, the ink particle, say 1 order of magnitude smaller than the space between the CNTs, and then the CNT spacing an order of magnitude smaller than the pillar size. So if I go up there from a few to 10 times that to 10 times that, I might be in the small optical wavelength. And we would love to do that.
I agree. That's what I thought looking at your SEM picture, the top head of it. I thought you could get somewhere like 200 to 500.
Yeah.
I wondered why you limited it down to
Yeah, that's just what we've done so far.
Okay. Last question, Mark?
Can you actuate the nanotube forests in any way? I mean, it might be cool to have this grid.
Yeah.
In some ways, you know, I could see, for flexographic printing, you want one stamp.
Sure.
But you could imagine having a little machine that changes the property of the stamp. You know, if you could actuate that with voltage or something.
Yeah, great idea. We haven't done that. We've thought about, for example, using electrowetting. Right? You could make a dynamic stamp in principle by electrowetting, so you just hold ink in certain pixels and then, yeah.
Cool.
Okay, let's thank John for